This next video does introduce some ideas from topology, mainly on open and closed sets. So it doesn't exactly mesh with what we're talking about and when we talk about new coordinate systems, for instance. However, it does kind of start to lay the foundation for what we will be discussing in this course when we get into kind of more theorems around differentiation. So it's good to have this knowledge as kind of a foundational piece to the course. So definition-wise, we're going to talk about open and closed sets here. An open ball of a certain radius centered at this point in this. So you might remember that when we were in Stewart, he was kind of interplaying points, or he was kind of using points and vectors interchangeably. So it's just saying at a point, really, a vector in place in space is defined as, and this is the notation we use, b subscript r0 for the radius. So a ball centered at x of a certain radius is the set of all points in n-dimensional space such that this is true. Now, in our course, we're going to be focusing on 3 dimensions, but we can extend it to n dimensions. So all this is saying is that the distance between our point and between our center and this point is less than a certain radius. Okay, so it's kind of the edge of this ball we don't have. So in R1 we would see this as, well, in R1 we're on the real line, and we would actually just have, okay, here's x0, and here is our x0 plus r, and then x0 minus r. Okay, real number line. Okay, in R2, I need a little bit more room for this one. R2, okay, you can imagine that we have our center, and then we go out a distance of r in every direction. Okay, so this is, and I'll just label this as x. Okay, so it's a circle. And then in 3 dimensions, we have, here's our point. We go from that point any direction, and we get a little sphere. Okay. And then so this is the idea of an open ball, and then how this manifests for us is when we talk about the idea of open. Okay, we talk about a set as an open set if we can take any point in that set. Okay, I'm just kind of translating this. So any point in that set, we can take a radius around that point. Okay, so a ball, we can make a ball around that point, and that point is that ball that we make is a subset of our set. Okay, and then we call that an interior point. Okay, another way of saying this is that, and I guess I'll just kind of fill in what I said here. This means we can draw an open ball around any point in U, in our set U, wow, and stay in U. Okay, that's kind of what it means. Alright, and then, well, if we talk about open, I imagine you might say closed. Okay, the way we define closed is just that the complement is open. Okay, now when we do this, there is a word of warning that I have, and all I want to say is that closed is not the same as not open. Okay, and we'll hopefully distinguish this in a moment here. Okay, so pressing on. I have a few examples here, and I want you to tell me if they are closed, or if they're closed or open, or are they both? Okay, pause the video and take a shot. Alright, so you pause the video, and here are the answers. First in the upper left here, this is going to be open unit disk without its border. Again, if you take any, you can think about always testing the open definition first. And that would just be if you think about everything inside that disk, you can always take a point in there and make a little radius around it and stay fully inside there. Okay. For the case where we look at the unit disk with its border, if we take the complement, so the region outside of that, so the two-dimensional space, just remove that disk. That is open, so that fits our definition of closed. R2, kind of for that reason, we can think of it as open because you can take any point in there, make a small radius around it, and it'll be within there. That's fine. And then the complement, which would be, if we take away R2, we get the empty set. The complement is open, and that one might take a little bit of thought. So if you take a point in the empty set, which is nothing, and make a radius around it, which is nothing, so radius around nothing is nothing, that is open. Okay, a little weird to think about. But then also for the reason that the empty set is open, that makes R2 closed. So R2 is both open and closed. Kind of weird to think about. Can happen. Okay. For the closed interval AB, well, it's closed interval, so it's closed. Okay. Again, think about it more formally. And when you look at this, so the first quadrant, including its axis, if you look at any place along either axis and take a little radius around that, it has to contain a point not in there, so it's not open. And if you look at the complement, it's not going to be, so the complement isn't open for the same reason. So that one, all we can say is not open. The half open interval is neither. This space, if you're having a little trouble visualizing it, okay, it's going to be, if you think about the line y is equal to x, and this is saying x is always less than y, that is going to be this space up here, okay, and that's going to be open. Okay, so just kind of buzzing through those. Then a few more definitions. So we have open, we have closed, we have open ball. We're going to talk about boundary points too. Okay, so a point is called a boundary point if every ball around this point of any radius contains a point in the set and not in the set. So a perfect case would be something like our example up here, where we're in quadrant 1 and we're looking along those axes. We have if we take a point on that axis, we get a point that is in our set of interest, like just to the right of the axis, but then we also get something to the left if we're looking on the y-axis. We get something that's not in our set as well. Okay, and then the set of all boundary points is called the boundary of that. Okay, so then for example, if we look at this set, the boundary of that is precisely just going to be the set of all points xy such that, so this is the unit disk without its boundary. This is just going to be the set of points xy such that x squared plus y squared is equal to 1. Okay, and then a nice theorem that we will end up using quite often is that if x is closed, x is closed if and only if it contains all of its boundary points. Very useful in solving proofs. So be on the lookout for that, and we're going to try to make use of that as frequently as possible. Okay, that's going to conclude the videos for this week.